All right, so let's recap a little bit of what we talked about last time. All right, so last time we talked about some things in the periodic table. I think you all have that down pretty good. We talked about orbitals, right? So what kind of orbitals did we talk about? We talked about s orbitals, which are shaped like what? Spheres, and p orbitals are shaped like dumbbells, right? Something like that, little figure eights. And we know that there's shading differences on the p orbital, right? And we also learned that these orbitals can hybridize to make different orbitals, right? And there's a whole series of hybrids. But for organic chemistry points of view, there's really sp3, sp2, and sp. How do we determine if a carbon or any other atom is one of those hybridizations?
Number of bonds.
Yeah, we look at the number of multiple bonds, right? So carbon will always have 4 bonds, but if it has single bonds, what would that belong to? That's sp3, right? If it has one multiple bond, what would we call that? sp2. And if it has 2 multiple bonds, right, we call that sp, right? And so we know that the shape of the sp3 carbon atom is what shape?
Linear.
Not linear.
Oh, wait, that's
It's trigonal, or excuse me, tetrahedral, right? It's tetrahedral. This one is trigonal, planar, and this one is linear, right? Now, what you need to know about these orbitals is what this really means. What does sp3 really mean? We didn't get to that last time. sp3 really means you take one s orbital and 3 p orbitals and you hybridize them together. And you get 4 new sp3 hybridized orbitals. Okay? So it means you take an s orbital plus 3 p orbitals gives you 4 sp3 orbitals. And they point towards the corners of a tetrahedron. Okay? So these orbitals are conserved. Notice there's 4 orbitals on this side. There's 4 orbitals on this side. What does sp2 mean? Right, it means you take an s orbital and 2 p orbitals to get 3 sp2 orbitals. Now wait a second, carbon has another p orbital, so what does that mean? That means it has one unhybridized orbital. Okay? So the carbon atom that's sp2 hybridized, here, there are 3 orbitals that are sp2 hybridized, and those form the trigonal planar geometry. But this carbon atom also has a p orbital that's not hybridized on it. And it reacts or interacts with the other carbon atom that's the same thing, and those p orbitals are what form the pi bond or the double bond. Okay? What does it mean to be sp? S plus a single p, right, gives us 2 sp orbitals. Which means then that the carbon atom on an sp hybridized carbon has 2 unhybridized p orbitals. That's why it can form 2 pi bonds. Okay? And so this is going to be important as we start talking about reaction mechanisms and other things. You have to be able to identify the types of orbitals. Okay? So, with that out of the way, let's jump in today into chapter 2. And we're going to pick up a little bit with some functional group talk. We're going to talk about types of acids and bases. We're going to talk a little bit about equilibrium. We're going to talk about what alters acidity. Not all acids are the same. And we'll talk a little bit about some basic reaction mechanisms. Okay? So, what we go over today is not the complete list of functional groups. We will learn more functional groups as we go on, but these are kind of the main functional groups that people come into interaction with early on. Alcohols. Alcohols have an OH group. The OH group is called a hydroxyl group. What does R mean?
Carbon.
Carbon. Yeah, it is an abbreviation that organic chemists use to mean any carbon group. Okay, that's not part of another functional group. I should preface that. Okay, so there are several types of alcohols that you all are very familiar with. This one is menthol. Okay, notice how that structure is drawn. We'll learn more about structures as time goes on. But you need to know a little bit right now. Each one of these points, or vertices if you will, represents a carbon atom. Okay? They're just not explicitly written out. So this is a carbon atom that is bound to the functional group OH, or hydroxyl. Okay? How many bonds can carbon have? 4. It's got a bond to oxygen, it's got a bond to this carbon, and it's got a bond to that carbon. That's only 3 bonds. What's the other bond? In organic chemistry, we frequently ignore hydrogen. There's actually a hydrogen there. If you look at a carbon like this and you go, I only count 3 bonds, the 4th bond is always the hydrogen. Okay, it's a shorthand that we'll learn about, I think in chapter 3 a little bit more. Okay? So that's kind of the nomenclature of how we talk about things. What kind of alcohols are you all familiar with other than menthol?
Ethanol, isopropyl.
Ethanol, right? So grain alcohol, stuff you like to drink. The other one? Isopropyl alcohol, right? Which is what? Rubbing alcohol, that's right. So it's called isopropyl alcohol or isopropanol. You buy it as a 70% solution at Walmart. Sometimes you can get it as a 91% solution. Ethanol. Okay. Beer, whiskey, wine, whatever your favorite beverage is. Okay. That's the main component, other than water. That's the alcohol functional group. Amines. Okay. Amine functional groups. There's a lot of amines in nature. Okay? An amine will have a nitrogen atom with its lone pair of electrons that is bound to 3 other things. Okay? You will have primary, secondary, and tertiary amines. The amine that is shown there, mescaline, which I believe that is peyote. I believe this is a psychoactive component of peyote. It has a nitrogen that is bound to only 1 carbon. What would we call this amine? Primary, secondary, or tertiary? It is a primary amine. Okay? So, if you have something like this, CH3NH2, that is a primary amine, and we write that as 1 with a little degree symbol. That's a primary amine. If I have a nitrogen that is attached to 2 carbon atoms and a hydrogen, what do you think we call that one? Secondary. That is a secondary amine. If I have a nitrogen attached to 3 different carbons, what would we call this one? Tertiary amine. Okay? So you can have primary, secondary, and tertiary amines. An amine always has a lone pair of electrons on the nitrogen. Okay? You can actually have 4 bonds to nitrogen. It becomes positively charged, but it is no longer an amine because it has no lone pair of electrons. Okay? It is then what we call an ammonium salt, which we'll talk more about later. Okay? Aldehydes. The aldehyde has what we call the carbonyl functional group, C double bond O. C double bond O is a functional group in and of itself that we call a carbonyl. And it belongs to a lot of other functional groups. Okay, so the carbonyl. And I'm just going to, we're not worried about what's attached yet. This is the carbonyl. If, however, you have a carbonyl that is attached to a carbon and a hydrogen, this is called an aldehyde. Okay? There's an example, cinnamaldehyde. It is the fragrant odor of cinnamon. Okay? I can take cinnamaldehyde, purify it, put it in a bottle. You can open it up and it smells like cinnamon. Okay? It is the oil that they give you to put in your little smell good stuff that you all put on lamps and other things, right? Put it in candles. If you have cinnamon smelling candles, they add cinnamaldehyde to that particular concoction. Right? So cinnamaldehyde. You can see the carbonyl that's bound to a hydrogen and bound to another carbon. Okay? That is the aldehyde functional group. We can also have a carbonyl that is bound to two carbons. So again, there's my carbonyl, but now it is bound to two carbons. This is called a ketone. It is not an aldehyde. It is a ketone. It has a different function. Okay? The example that they give you is the fragrant jasmine. Where do you think that comes from? Jasmine. Yeah, the jasmine flower, right? So you get this particular molecule. It has a ketone, and it is fragrant, right? People use it for a variety of different things. Okay? The example that I have written up here is acetone. This is your fingernail polish remover, your paint thinner, whatever you want to use it for. Okay? It is a ketone. It is not an aldehyde. Okay? We can also have a carbonyl that appears to be attached to an alcohol and a carbon. This is not an alcohol anymore. This whole thing is the functional group, and it is called a carboxylic acid. Okay? The example that I've drawn up here is called acetic acid. What is acetic acid used for? Where have you come into contact with acetic acid? We've probably come into contact with it in chem lab. I'm talking about in your everyday life. How many people like Italian salad dressing? What does Italian salad dressing have in it? Vinegar. Vinegar, the acidic component of vinegar is acetic acid. Have you ever heard of a bottle of wine going to vinegar? It's because ethanol can get oxidized over time to acetic acid. It gets transformed. So if you don't cork your wine bottle correctly and you let a lot of oxygen into it, the ethanol gets converted into acetic acid. And we'll talk about those types of reactions later on in the semester. The point that I'm trying to make there is that one functional group, an alcohol, can be converted into another functional group through chemistry. Okay? And in fact, that's what your liver does with ethanol when you drink a beer, drink a glass of wine, whatever. Your liver converts it into first an aldehyde that then ultimately gets oxidized to a carboxylic acid. And we'll talk about that chemistry this semester as well. This functional group turns out to be very important for something you all probably take after this class, right? Ibuprofen. What is ibuprofen useful for?
Inflammatory, painkiller.
Yeah, it's a painkiller. It's an anti-inflammatory. People take it to help reduce fever. People take it because they get a headache, right? So you leave class, you got a headache, you might take some ibuprofen. If that is not that functional group, if it did not have the carboxylic acid functional group, it would not work. It's very important that that functional group be there, okay? Now you might say, well, that's a carboxylic acid. Why can't I just drink a little vinegar? It doesn't work. You got to have the other stuff with it too, okay? We'll learn a little bit about that this semester as well, okay? But the carboxylic acid is a very important functional group. We can also have a functional group called an ester. Notice it kind of looks like a carboxylic acid except for what? Right? It's got a carbonyl, it's got an oxygen, but instead of a hydrogen, it's got another carbon, another R group, right? It can be anything out here. This is called an ester, okay? And the example that's there is methyl salicylate. That comes from the oil of wintergreen. So if you like wintergreen kind of flavoring stuff, they add methyl salicylate to whatever it is to give you that artificial flavor. But one of the things that you need to know about esters, since they kind of look like carboxylic acids, but they're not, they do have some similar chemistry. They're just not acids. We'll learn about that chemistry as well. Esters typically are pleasant smelling. Carboxylic acids, nobody splashes on acetic acid before they go out on a date, right? I mean, nobody wants to smell like vinegar, okay? But almost all of your perfumes and colognes will have esters in them because esters are a more pleasant smelling molecule, okay? So esters are typically pleasant smelling. Carboxylic acids are usually quite offensive in terms of their smell, okay? We also have the amide functional group, okay? And what you can see here, you will have a carbonyl that is bound to a nitrogen. So it looks like a carbonyl plus an amine come together, okay? This is called the amide. The example that they give you up there, I'm not so sure why they did that, LSD. But if you look at the name for LSD, lysergic acid diethyl amide, it's giving, the name is coming from the fact that it has the amide functional group. That's got other functional groups, right? It's got a tertiary amine and another tertiary amine, some other things in there involved as well. But it's that amide functional group that's responsible for the psychedelic effects of LSD. Okay. What else do you all know that might be an amide? You all come into contact with these things all of the time. If you use anything made of nylon, nylon is a polymer that is composed of the amide functional group. Okay? Nylon's a very strong fiber. We like to make ropes out of it. We make stockings out of it. We make all kinds of things out of it. It's resistant to weather. It holds up well in the sun. Right? It's pretty good. Your proteins, the proteins in your body are held together with amide bonds. When you get to biochemistry, they're going to call those peptide bonds. But it's the same thing. It's just an amide. Okay? And the fact that amides are very robust functional groups, they don't degrade very easily. Kind of nice. I like to know that my proteins will hold together. Right? I don't like to just fall apart. Right? We are polyamide based, not polyester based. And there's a reason for that. Okay? So, those are the main functional groups that you need to know now. As we go into different chapters, we'll learn a few more functional groups along the way. But these are the functional groups that you need to know by next week. Okay? You need to know each and every one of those by sight and name. So it would be fair for me to come in and say, identify the functional groups. Okay? I'm going to start talking about the chemistry in terms of functional groups. When I say, well, if we took a carboxylic acid, you need to know what that looks like. Okay? You got to start committing that to memory. I want you all to pair up, get into groups of 2 or 3, and I want you to look at that molecule and identify all of the functional groups that you can at this point. I'll give you 2 or 3 minutes. So pair up into groups. find it?
I see 3 esters, I think. So on the top, the very bottom, and one at the very bottom. As for the middle, I can't tell, but the middle is what? Yeah, you're right. I think I'd call it like a color.
All right, folks, let's return to normal order, so to speak. So, I'm going to take my cursor here and we're going to just start from left to right. What functional group do we have here? That's a carbonyl. It's not a ketone yet, but what is this? It's an amide. Yeah, amide, right? That's a carbonyl attached to a nitrogen, right? What functional group do we have here? That's an alcohol. We've got a functional group here. What is this one? That's an ester, right? I'm going to skip over these because we haven't talked about those yet. What's about this one here? It's another ester. What do we have here? What did I hear the first time? It is a carbonyl, but which functional group does it belong to? That's a ketone. That's right. See, we got a carbonyl attached to 2 carbons. Right? What do we have here? We've got another alcohol. What do we have here? Another alcohol. Down here we've got an ester, and we've got another ester, right? And we've got some other functional groups here that we haven't talked about yet, and that's okay. But you can see that with just a handful of carbons and some hydrogens and oxygens, you can put together these in different orders, different arrangements, if you will, getting different functional groups and having a very powerful drug called Taxol, right? It's one of the most potent anti-cancer drugs that we know of. But you've got to have all of those functional groups. And not only do you have to have all of those functional groups, you have to have them exactly in the right place, pointing exactly the right way in space. Okay, and that's the tricky part. I can get all kinds of stuff together that has all of those functional groups, but they're not put together correctly, right? So it's not just about having the functional groups, it's about having the functional groups in 3 dimensions so that they point in the right way, so that when they interact with the cancer cell, so to speak, they can do what they need to do, okay? So, it would be fair game on an exam for me to give you a molecule and ask you to identify the functional groups. Okay? In fact, I can guarantee you that's going to happen. Okay? So, or I can give you a big molecule and point to some place and say, what's that functional group? And you need to be able to do that. Okay? All right. So, let's get into acids and bases. There are 3 types of acids and bases. And you'll notice that I have kind of made things different sizes. Why do you think I did that? Importance. From my perspective, the first 2, the small one and the medium-sized one, I'm just going to talk about with you for historical purposes. All right? I don't even really know why we still teach it other than for history. Lewis acids and Lewis bases really account for pretty much so all of chemistry. Okay? I've got some friends who would argue with me. I think they would lose the argument. But nonetheless, and the reason is because Lewis acids and Lewis bases can explain the Bronsted-Lowry acids and bases. And they can explain the Arrhenius acids and bases. Okay? So an Arrhenius acid is anything when you dissolve in water, it makes hydronium ions, H3O+. Okay, so if I take a substance and I put it in water and it makes H3O+, it's an areneous acid. If I take something and I throw it into water and it makes hydroxide, OH-, like sodium hydroxide, potassium hydroxide, things that you work with in Gen Chem, that's called an areneous base. Okay? That's an old definition. And chemists realized, you know what, that doesn't explain everything. We've got things that have an acid character to them, but they don't make H3O+. They don't make hydroxide. There's got to be a better definition. Then along came Bronsted and Lowry, who tried to do this, and they said that a Bronsted acid is a proton donor, an H+ donor. Okay, so we call that a proton, H+. Why do we call that a proton? Because remember, a hydrogen atom only has a proton and an electron. So if it's H+, it's just that nuclear particle. Okay? So anything that can donate a proton to something, Bronsted and Lowry said, well, that's an acid. Okay? They also said that anything that accepts a proton is a base. What's the focus of their theory?
Hydrogen?
Yep, proton. Yeah, the H+. Okay? And it works for a lot of things. If it donates a proton, it's an acid. If something accepts a proton, it's a base. Makes sense. The problem is that there are acids and bases that don't donate protons or accept protons. It doesn't explain everything. Then along came Lewis. G.N. Lewis died in the, I don't remember when he died, probably in the late 1930s, early 1940s. One of the people who probably should have gotten a Nobel Prize but didn't because he was a jerk, according to the rumors. You all learned in general chemistry, Lewis structures, same guy. Okay? But G.N. Lewis came up with his theory in the early part of the 20th century, and we have what are called Lewis acids and Lewis bases. What did I tell you on Tuesday chemists focus on? What is the main thing that we focus on? Carbon. No, organic chemists focus on carbon, but in chemistry in general, what is the thing that we focus on? Electrons. Right? What do you think the Lewis theory focused on? Electrons, right? And so it really is the theory that really accounts for everything. So Lewis said that a Lewis acid is anything that accepts a pair of electrons. Okay? And Lewis also said a base is anything that donates a pair of electrons. And guess what? Lewis acid, Lewis base theory explains Bronsted-Lowry and Arrhenius all at the same time. So we've got three theories when you only really need one. And that one is Lewis. And so we're going to spend most of our time in class really talking about things from a Lewis acid, Lewis base perspective. If you understand Lewis acidity and Lewis basicity, you can understand 95, 96% of all chemistry. When you get into biochemistry and you start talking about how things interact, it's going to be largely because something is functioning as a Lewis acid and something else is functioning as a Lewis base. And you start to get those acid-base interactions. Okay? So this theory is very, very important for you to actually understand as best we can. Okay? So let's look at some examples. Water has this structure. They draw it linear there. I don't know why. That's bad form. Right? Can react with this molecule called amide, which it has a negatively charged nitrogen. Okay? And you get an equilibrium, right? And you get hydroxide plus ammonia, NH3. Okay? This is an acid-base reaction. This is functioning as the acid. This is functioning as the base. Okay, how do I know that? When I look at what's happening, I know that this proton is no longer on water over here. It just makes hydroxide, right? I know that this only has 2 protons and now it has 3. So I know that this proton has to go from here to here. Okay? So that's why we can consider this a Bronsted acid, and we can take this as a Bronsted base. However, I don't like looking at where protons go. I like looking at where electrons go, right? And so what happens is electrons are always responsible for the chemistry. So this pair of electrons can react to grab that proton. And these electrons that are making the bond between oxygen and hydrogen can go on the oxygen. So these electrons come here to give me another pair and give me a minus charge, right? This nitrogen picks up that proton and I get NH3, okay? Notice how I'm drawing these arrows. This is going to be very important when we get to reaction mechanisms. Where is my arrow starting on the nitrogen? Where is it starting? At the pair of electrons. We call this electron pushing. I'm pushing this pair of electrons, and I know it's a pair because I'm drawing a double-headed arrow. Okay? Each side of the arrow means 1 electron. Okay? And that means I'm forming a bond between this nitrogen and this hydrogen. Notice here I'm starting with the electrons that are in the bond, and I'm moving them from the bond onto the oxygen atom. Okay? This is called the electron pushing formalisms. Okay? We'll learn more about this. But this is nothing more than an acid reacting with a base. Okay? Acids react to give conjugate acids. Bases react to give conjugate bases. Where do you think the equilibrium lies? Do you think the equilibrium goes to completion and it's over on the right? Or do you think this reaction doesn't hardly go at all and it lies to the left? Okay, it's a hypothesis that we can test, right? How do we measure the equilibrium? What did we learn about on Tuesday? How do we express it? KEQ is equal to what here? How would I write the expression? Play hangman a little bit here. I'll give you a bracket. Or am I going to put in the bracket? Pardon? Okay, it's the products. The products are the hydroxide and the ammonia, right? We'll multiply those together. Over what? The reactants. It's a minus charge. Okay? So all I've got to do to determine where the equilibrium lies, right, is I got to go into the lab, I got to figure out how much of this I have, how much of that I got, how much of that I got, and how much of that I got left at equilibrium, right? Does that sound easy to do? No, I'm not going to let you just go over to the lab and figure this out during an exam, am I? We're going to have to figure out how we can look at that equation and know which side of the equilibrium is favored in this reaction. We're going to learn about that when we talk about acid strengths. But what you need to know right now is that an acid-base reaction always favors the side of the reaction with the weaker acid or weaker base. Nature does not react to give things that are stronger. It reacts to give things that are weaker or more stable. Okay? The reaction side will be favored. The favored side will be the one with the weaker acid and weaker base. Okay? Now, it turns out, in this particular example, hydroxide is a weaker base than amide. So which way does the equilibrium lie? To the products or to the reactants? products. In fact, this reaction, the equilibrium constant would probably be in the millions. And so it lies so far over to the right, we say it goes to completion. We say that the reverse reaction is essentially non-existent. Okay? You're going to learn how to look at reactions and make these kinds of approximate decisions. You don't always need to know a value to 3 decimal places to make a decision. Okay? When you get into biochem, you need to look at something and say, that's going to be more stable than that, so it should favor this side. And we're going to, hopefully you get some of that experience in this class so that you'll be ready for that. Okay? So, we also have an example here where we have hydrochloric acid, HCl, reacting with methanol. Methanol is just wood alcohol. And this is also an acid-base reaction. Okay? Where you end up with chloride just being the conjugate base, and the protonated methanol, if you will, being the conjugate acid. Okay? We'll learn about these things as well. So there's all kinds of reactions that will come into play. In fact, reaction number 2 will be important in a reaction mechanism in one of the chapters where we start talking about substitution reactions. Okay? So having an understanding of how acids and bases play out is going to be very important. Okay? All right, let's look at some of the acids and their conjugate bases. This is from table 2.1 in your book. You do not have to memorize this table. Having said that, you need to kind of internalize the table and know kind of rough ranges. Okay? You kind of need to know some rough ranges. What you need to know is that strong acids always have weak conjugate bases. That makes sense. Here's why that makes sense. If I'm a strong acid and I'm dissolved in water, it means I like to get my protons up, right? You all learned about this in Gen Chem a little bit. HCl is a strong acid. Why is it a strong acid? It's a strong acid because when you put it in water, it completely dissociates. Okay? If chloride was a strong base, it would never dissociate. The chloride would just hold on to the proton. Okay? But chloride is actually a very poor or very weak base. And so, go away. Go on, hydrogen. You can leave, right? So things like hydrogen iodide, hydrogen chloride, HBr, H2SO4, nitric acid. These are all the things that you learned about in general chemistry that were strong acids. You need to just know those are strong acids. You also need to know that there are really weak acids, things like alcohols. Water's a weak acid. Kind of need to know those ranges. Okay? Where are the carboxylic acids? Right there's acetic acid, right? Where would you say that is in the list? Kind of in the middle, right? So carboxylic acids aren't strong acids, but they're also not weak acids. Okay? That's why we find them in a lot of things like medicines. Okay? Not too strong, not too weak. They can do the chemistry that they need to do. Okay? So things in the middle here are going to be important as well. Okay? So anything that has a weak conjugate base, by definition, is going to be a what? A stronger acid. And anything that has a strong conjugate base, by definition, is going to be a weaker acid. Yeah, very good. Okay? Very good. All right. So we have to have a way of expressing this. We've already talked a little bit about the equilibrium constant, KEQ, right? So we have our generic acid reacting with our solvent, in this case water. So let's say we're adding HCl or whatever to water. We get an equilibrium, right? It dissociates, we make hydronium, we get A-. We can write the equilibrium constant as the concentration of products over the concentration of reactants, right? That's KEQ, that's what we just talked about. What happens to the concentration of water when I put hydrochloric acid into it? Does it go up or does it go down? According to this, what happens? Right, so I've got pure water. I'm starting off with a container of pure water, and I'm going to throw in some HCl. say a milliliter of HCl, what happens to the water?
Doesn't it donate?
It donates an electron pair, and it picks up the proton, that's right. But what happens to this water? It becomes what? It becomes the hydronium, the H3O plus, right? So what happens to the amount of water I have in my flask? Does it go up or does it go down?
Down.
It goes down a little bit, right? It goes down a little bit. And so the water concentration should change a little bit. But wait a second. Does anybody know what the concentration of pure water is? If I give you a glass of just pure water, what's its concentration? Water is dissolved in itself, right? So we can express it as a, pardon?
100?
You're close, a little over. It's actually in the mid-70s, 75-ish, 75 molar. So if I add just a little bit of hydrochloric acid to that water, did I really change the concentration of water that much? Not much, right? Not much. It's hard to get anything more concentrated than pure water. Okay? So if the concentration of water really doesn't change much, do I really need to pay attention to it here? I really don't, right? And you all were taught in general chemistry, and you were probably taught in high school if you had a chemistry class, that pure liquids can just fall out of the equation. Again, you were told a lie. Things don't just fall out of the equation. If you have an equation and something falls out, it is no longer equal. It can't be that way, right? But what we can do is we can do a little mathematical trick where I take this side of the equation and take it times the concentration of water, and take this side of the equation and take it times the concentration of water, and I can make it cancel out, okay? And so we end up with what's called an acidity constant, Ka, which is the equilibrium constant times the concentration of water, okay? And we just call it Ka. So if you see expressions for Ka is equal to H3O plus, A minus over HA. It looks like water fell out of the equation. That's nonsense. I've just combined it in to the Ka constant, okay? We played a little trick. Now, if I have a strong acid, what would you expect the value for Ka to be? Large or small? Okay, so if I have, let's do the reaction, right? HA plus H2O gives A minus plus H3O plus, right? And Ka is equal to H3O plus times A minus divided by HA. If I have a strong acid, that means this is going to completely dissociate, right? And it's going to completely form this. So these numbers are going to be big. These numbers, or this number is going to be tiny, right? When I have something big times something big divided by something that's tiny, what do I have? If I take 1,000,000 and divide it by 0.01, is that going to be a big number or a small number? It's going to be a very big number, right? So when values for Ka are large, we have strong acids. If I have a weak acid, very little of this dissociates. So these numbers would be small, this number would be large. When I take a small number and divide it by a large number, I get a very small number. So weak acids will have small values for Ka. Okay? The problem is that chemists, when it comes to math, we are extremely lazy. We don't like dealing with a lot of numbers, oddly enough, even though you might think in gym game you dealt with a lot of numbers. Nobody likes to write 1,347,000, blah, 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 blah. So what chemists do is we do what we call taking the negative log of that number so that we can deal with numbers more easily, okay? So for example, the typical organic acid, things that typically have acid behavior that are organic, they typically have Ka values of 10 to the negative fifth to 10 to the negative 50th. Okay, so 10 to the negative fifth is 0.001. 10 to the negative 50th is 0.001, right? 49 O's and a 1, right? So, do you want to write all that out? Do you want to punch all that crap into your calculator? You don't, right? So what we do is we take the negative log of those numbers. Anytime you take a negative log of something, it simplifies it, okay? Negative log is called P. And you can P anything, okay? But we're going to pKa. So when I say pKa, that means taking the negative log of that acidity constant. 10 to the negative 5, when I take the pKa of that, or take the negative log of that, I get 5. I would rather work with the number 5 because I've got 5 things on my finger as opposed to 10 to the negative 5, which I don't have any of, right? I can think about that number better. 10 to the negative 50th becomes 50, okay? So, the important thing to note here is that since I'm taking the negative log of these numbers, okay, the smaller the number, the stronger the acid. So 5, a pKa of 5 is a stronger acid than a pKa of 50. Okay, so strong acids will have small pKa values. Weak acids will have large pKa values. Okay? Any questions about that? Okay. So, there's our equation. You need to know these things. If Ka is greater than 1, that means that the ionized products will be greater than the intact acid. How many people have a calculator handy? All right. Punch in the number 1 and take the negative log of it. It's what? It is 0. That is right. Now, so anything, so again, that's 0 is small, right? Right? So Ka's of 1 or greater are going to give you small numbers. Right? What happens if you have a Ka of 2? What would that give you in the calculator? What's the negative log of 2? Negative what? Negative point what? 0.3. But it's becoming negative. Right? So the more of this I have, the bigger this becomes, the more negative this number is going to become, or the pKa of that number is going to become. Okay? When Ka is less than 1, we know that it favors the starting materials. This is going to be weak acids if Ka is less than 1. If Ka is much greater than 1, and typically we say if it's greater than 1,000, we say it goes to completion. Okay? Everything gets converted to products. And if Ka is less than 1,000th, or 10 to the negative third, we say that the reaction doesn't go hardly at all. Okay? So there are some ranges that you need to kind of commit to memory. It'll help you out with that. Okay? So here's a table. This one isn't in your book, but this gives some pKa values. Okay? Hydrochloric acid, you all learned in general chemistry, that is a strong acid. It has a pKa of -7. Is that a big number or a small number? That's tiny. This is acetic acid. This is vinegar, right? It has a pKa of 4.8. Okay, that's a bigger number. So is this a weaker or stronger acid than HCl? This one. This one is weaker, right? Larger numbers being weaker acids. I can drink this. I cannot drink that. Okay? Water has a pKa of just under 16. Notice alcohols. They also have a similar pKa, don't they? Alcohols are about as acidic as water. Not quite, water's a little more acidic. It's a little smaller number, but alcohols are about as acidic as water, which means I would expect water and alcohols to have similar chemistry, and they do, okay? What's the hybridization of this carbon? That's sp. Notice that these hydrogens have a pKa of 25. Is that a strong acid or a weak acid? It's a weak acid relative to everything else we've been talking about. But what about for methane, CH4? It has a pKa of 50. So if I compare methane and acetylene, don't worry about the names yet, which one's the stronger acid? Acetylene. What's the difference? Is it double? Remember, it's pKa, right? Now, you're right, it's double in terms of the numbers that are shown there. But remember, we're taking the negative log. Every unit that you have is an order of magnitude. This is 25 times more acidic than methane. Acids and bases will drive you crazy because it's all about relative. It's a relative argument. It's not an absolute. You always have to compare two things, okay? But I do not expect you to memorize all of these values, but I do expect you to know that things that like carboxylic acids are typically the strongest acids in organic chemistry, that alcohols are pretty close to water, and that hydrocarbons can have different acidities. Okay? You kind of need to know those rough government numbers, if you will. Okay? All right. So what makes something a stronger acid than something else? There are 4 factors that affect the acidity of anything, and they are listed here. There's the element effect, the inductive effect, the resonance effect, and the hybridization effect. Okay? All of these things can influence the acidity of a molecule. We're going to talk about each one of them. But the take-home message here, I don't care what the effect is, anything that makes this A- more stable, anything that makes this more stable will mean that the equilibrium is going to favor the product side. It's going to make this a stronger acid. It's all about the stability of the counterion. Remember, weaker bases make for stronger acids, right? Weaker conjugate bases. What would make this a weaker conjugate base? Stability. If I can make this stable, it's going to make this a stronger acid. Okay? So you're always going to look at the conjugate base, and you're going to ask yourself, what's going on with it? What makes it stable or unstable? Okay? And so the more stable the conjugate base, the more acidic the acid. Okay? So let's look at these effects. The first effect that we need to talk about is called the element effect. This is when we're looking at things in the periodic table. So if we remember the periodic table, right, there's carbon, nitrogen, oxygen, and halogens, or fluorine. As we go from left to right in a period of the periodic table, we go from left to right. What's happening to the acidity? It's increasing. HF is a stronger acid than water or alcohol. Alcohols are stronger acids than amines. Amines are stronger acids than hydrocarbons. So as I go from left to right in the periodic table, I'm increasing in acidity. Okay? From left to right. And why does that make sense? Right, if I'm wanting to compare methane, CH4, to HF, I need to look at the anions, right? Well, if I remove one of the hydrogens, right, then I've got carbon with a negative charge. And if I remove the hydrogen here, I've got F minus. Which one of those is the most stable? F minus or C minus?
F minus.
And why?
Closer to the.
What do we know about fluorine?
It's the most electric.
It's the most electronegative, so it would like to have a negative charge, wouldn't it? It would like to pick up a little electron somewhere. Where does carbon sit in the electronegativity? It's not anywhere near the electronegativity of fluorine, so having it hold on to a negative charge is less stable. It would rather react with something. Fluorine, fluoride, hey, I'm happy. I'm just fine having that extra electron, right? So going across a period from left to right increases acidity. In a family, it's going from top to bottom, okay? So HF has a pKa of 3.2, whereas HBr has a pKa of -9. HF is not a strong acid by definition. It is a nasty acid. It will dissolve your flesh and eat your bone, but it is not a strong acid. Okay? It is the weakest acid of the halogen family. Okay? And what happens as we go from top to bottom in a family? The atoms get bigger. So I'm putting that negative charge on fluorine to make fluoride on a small particle, and on bromine, it's a big particle. And it turns out the more surface area that the negative charge can be delocalized on, the more stable it is. So larger anions are more stable than small anions.
So you're saying, so from left to right it increases acidity, and then from top to bottom it decreases?
It increases
Oh,
in
increases
acidity.
also.
Yep. So HF, HCl, HBr, as we go down, we are getting stronger in acidity. Okay? So that's the element effect. It increases from left to right in a period, and from top to bottom, it increases in a family. Okay? And so you can see the values here. HF is 3.2, HCl is -7, HBr is -9, and HI is -10.
Yeah, I'm a little confused. So the larger the molecule is, the heavier it is, the more acidic it is, right?
The larger the anion, yes.
Yeah, as it goes down the list, but also the most electronegative it is, the more acidic it is, right?
If you're talking about comparing things within a period, yes.
Oh, within a period.
Yeah. Iodide is not more electronegative than fluoride.
All right, I understand.
So electronegativity is in a period, size is in a family.
How does acidity correlate to corrosiveness? Like, how can we tell how corrosive something is?
The corrosive nature of acids not only deals with its acidity, but also its anion. So most acids are considered corrosive by nature. In fact, even weak acids can be corrosive. Ethanol, beer, is corrosive. Take alcohol, put a nail in it, it will corrode.
So in the same way that electronegativity has an upward diagonal trend, the acidity has a downward diagonal trend on the periodic table?
Yeah, I think you could think of it that way.
Okay.
To a degree, yeah. Okay. So, that's one trend, element effect. The inductive effect, people get this confused with the element effect. Okay, but it's not. So the inductive effect is the pull of electron density through sigma bonds caused by electronegativity differences in atoms. And that's where I think people get confused. So when we look at ethanol, I'm going to draw it out. CH, H, H, CH, H, O, H. Okay, there's ethanol. And we can also have trifluoroethanol, where the first three hydrogens are replaced with fluorine. Notice the pKa differences. pKa of 16, pKa of 12.4. This is the stronger acid. Why is that? Well, I have to look at the anions. So if I imagine them losing their hydrogen, right? It's not the element effect because the negative charge is on the same element in both of them. Oxygen is oxygen. But there's something going on with these fluorines that's making this more stable. What could it be?
It's pulling it closer to the
Close. So what's happening? Let's think about it. What are the fluorines doing that the hydrogens can't do?
Or electronegative.
Much more electronegative, right? Hydrogen and carbon have almost the same electronegativity.
sharing electrons.
So what do you think about those covalent bonds between carbon and fluorine? Are they nonpolar or polar? They're very polar, right? So remember, in some of your homework, you had to figure out the polarity of bonds, right? So fluorine is going to be partially negative. This fluorine is going to be partially negative. This fluorine is going to be partially negative because they're pulling the electrons from these bonds to themselves, right? What's that going to do to that carbon? If we're sharing electrons and I pull electrons towards me, by definition, that makes you more what? Okay, weak, but what do we mean by weak?
A little more surface area.
Maybe a little more surface area, but what else? If there's partial negative charges on the fluorines, does the carbon have to have? Partial positive, right? And so that's going to make this carbon partially positive. Okay? Well, that carbon wants electrons. Where's it going to get them? It's not going to win from fluorine, right? But what could it do? It could pull from its neighbor, right? So maybe it pulls electrons closer to it. And when it does that, what does that put on this carbon?
Negative.
Now, if it's pulling electrons this way, what does that do here? Gives it a little bit of a positive charge. And what happens when you put a little bit of a positive charge next to a negative charge? They attract. And is that a good thing or a bad thing? It's a good thing. Opposite charges stabilize each other, right? So this anion is stabilized by this small amount of positive charge that's next to it. This one doesn't have that. This becomes a more stable A minus, if you will. This one becomes a less stable A minus, and that's why this is a stronger acid than this one. Okay, so that is the inductive effect. Okay, and you can see the examples shown there. I just drew that on the board for you. Okay. There is also the resonance effect. If we look at the pKa of ethanol versus acetic acid, we can clearly tell that acetic acid is a stronger acid. 4.8 is a much smaller number than 16, right? So, how do we account for that? Well, again, we look at the anions. So, and I just drew, so let's draw that out again. And I'm just going to draw the anions. So this came from ethanol. This is from acetic acid, the anion. Negative charges on oxygen, negative charges on oxygen. Can I make a decision? No. They have the same element, right? So there is no element effect. Do I have any fluorines anywhere? I don't. So it's not the inductive effect. But what I can do here, does this negative charge really belong only to this oxygen? No. I can draw a resonance structure for this. And we talked a little bit about resonance structures last time. Okay. And so now that I have another resonance structure, that's why this is more stable. The more resonance structures you can draw for something, the more stable it is. It's like delocalizing those electrons over a larger area, just like when we were going down a family, right? If I take a negative charge and I spread it out over a larger volume of space, that stabilizes it. Okay. And so acetic acid is more stable, or excuse me, the acetate anion is more stable because I can draw a resonance structure for it. I can't draw any resonance structures for this. If I tried to push these electrons in here, I would break the octet rule for carbon. All of the electrons are on oxygen. All of these electrons are delocalized over 2 oxygens. Okay? Much more stable situation. All right. The last effect is called the hybridization effect. And here we've got ethane, ethylene, don't worry about the name so much, and acetylene. And what you notice for the pKa is the pKa of ethane is around 50, the pKa of ethylene is 44, and the pKa of acetylene is 25. What's happening to the hybridization of those carbon atoms as I go from left to right here? What's the hybridization of the carbon atom for ethane? sp3. Ethylene? sp2. Acetylene? sp. Right? So, what does that mean? That means that ethane, since it's sp3, the hybrid orbital is 25% s character. 1 s, 3 p's, that means 25%, right? Ethylene, sp2, means that the hybrid orbital is 33% s character. And acetylene, since it's sp, it's 50% s character. Why would putting a negative charge on an atom that has more s character stabilize it? What did we learn about the s orbital? It's a sphere. Does it have a node? Those electrons can get really close to the nucleus. What about a p orbital? It does have a node, and where is that node at? In the center, at the nucleus. So, if I'm putting electrons in something that has more p character, they can't get closer to the nucleus. And putting electrons closer to positively charged nucleus should stabilize it, right? So you're going to see that sp3 hydrocarbons are going to be much less acidic than sp2 hybridized hydrocarbons, much less acidic than sp hybridized. And it has to do with the percent s character in the orbital, okay? And you can see this in these neat little graphics. Remember that the more red, the more negative, right? And so you can see in the sp3 hybridized case, there's a lot of red, meaning that there's a lot of negative charge. You can see that the red starts to fade, and when you get to this, it kind of fades off because these electrons are actually closer to the nucleus, okay? Here they are further apart. If you actually took your ruler and measured out to the edge, you'd see that that's further apart than that. And that's actually pretty close. So these electrons are getting closer and closer to the nucleus. All right. We will do some more examples of this on Tuesday. We'll do some examples on the board before we jump into chapter 3. And we'll cover this in a moment. But for today's quiz, I want you to turn in problem 1.51. Rip it out of your book. On the front, print. Please print your name so I can read it legibly. And also write your ID number on it in case I can't read it. Okay? You can do multiple. It's easiest if you just do one. And you just on your way out, just put them over there at the desk on the edge. And I will see you all next week. You all have a good weekend.